right, we are now ready to move into the next phase of the course where we've been spending a lot of time talking about what are called rates of change, slopes, we've also called them derivatives. We want to look at the nice part of calculus and the ways that we can shorten up this process that we've been working with the last few days. And what I mean by shortening up the process, there are certain equations or certain functions where finding the derivative is a lot easier than going through that definition of derivative that we had before. Okay, now I'm going to remind you of what we've been talking about though. Okay, we've been working a lot with this definition right here. And basically this definition of derivative has helped us to find the slope of a function at points, at certain locations. Right? Now, what we want to do is find out, are there some equations where we don't necessarily need to go through all of this work? Because there's a lot of algebra involved, there's lots of chances for mistakes along the way. And the answer is yes, there are some equations where we have the ability to shorten up this process, and that's what we want to start the discussion on today. Start looking at which equations do we have a shortcut for. Okay? The first group of equations that we have a shortcut for are what we call polynomials. Okay? And so I want to look at an example of a few of these different types of polynomials to look at the shortcuts that we can use. Okay? All right, what if I gave you the equation f of x equals 3x? Okay, this is a polynomial. It's a linear equation. It's a very basic polynomial, but it is a polynomial. Okay? Now, even without doing any of the work up above here, let's just talk about what the answer to this should be. You know, if I know that this is my function, what should be this function's derivative? What's another name for derivative? Slope. What is this function's slope? 3. So the answer for this derivative should be 3. So even before we do any work, if we know that we have a linear equation, even if it's, you know, f of x equals 3x plus 6, what should be my derivative function over here? What's the slope of this equation? Well, it's still 3, isn't it? Okay? So therefore, if we ever have a linear equation, is it really necessary to go through all this work? And the answer is no, because we know derivative is just a slope, so we just have to look for the slope of this function. We've got our answer. Okay? So linear equations, we don't really need to go through the process. Okay? Another type of polynomial. What if I give you the equation f of x equals 5 or y equals 5? Okay? What type of graph do we get for this? Close. Horizontal. Yeah, straight horizontal line. And what is the slope of a straight horizontal line? 0. So again, we don't really need to go through all the work for this one. We can just visually look at the function and say, well, that's a straight horizontal line, got to have a slope of 0, so I know my derivative function is 0. And again, this will be true no matter what I choose. If I choose f of x equals -7, doesn't matter. It's still a horizontal line, so its slope is still 0. So again, don't necessarily need to go through all the work because we already know what this is if we just think about what a slope or a derivative really is. Okay? The ones that we really do want to spend some time on, though, what if we get up to higher degree equations? So what if we get up to something like 4x squared? Okay? What do we do in this situation? Okay? All right, well, let's go ahead and run through one example here using this limit definition. I think you will start to see the pattern here pretty quickly if you don't already know it. Okay? All right, we want to take the limit as h gets closer to 0. Okay? 4 times x plus h squared minus 4 times x squared, all divided by h. I'm just using my definition that we've been working with the last few days. Okay? When I start to multiply this out, again, we've done a lot of these, so that's why I'm just going ahead and doing all the work at this stage. Okay? I'll end up with 4x squared plus 8xh plus 4h squared. Okay? When all this is multiplied out and you clean it up, okay, this is what you'll end up with. And if you need to, just off to the side, you know, when you're looking back at your notes, you can work through it if you're not convinced this is right. Okay? But this is the correct for the first one. And then minus 4x squared all divided by h. Okay? So we're just setting up this definition of derivative. We notice that the 4x squared and the negative 4x squared cancel. And then we notice that every term left in the numerator still has an h in it. We can factor out that h and cancel it off with the h in the denominator. And what will I have left then by the time I'm finished? 8x plus 4h. Right, exactly. Okay, so this is what I get when I do all the algebra and clean it up. Okay? Now, the last part of this then is we want to take the limit as h gets close to 0. Okay? Actually, we can plug in 0 here, can't we? Because we don't get division by 0 or anything else goofy like that. So we end up with a final answer here for this derivative function of 8x. Okay? All right, now, here's the thing that I want to point out, is that what if I change this from a 4, what if I change it to some other number? Okay? So what if I change this 4 to a 5 or something else? What is going to be changed in our process here? Okay? Well, first of all, both of these 4s will turn into 5s, won't they? Okay? So I'm just going to rewrite this. I just want you to see how similar this is so we can notice the pattern here. So both of those turn into 5s. Okay, this term canceled off with this term anyway, didn't it? Even if they're both 5s. Okay? What does this number become when this is a 5? This is now a 10, and this is a 5. Okay, so this is a 10 and a 5. Okay? By the time we keep simplifying, what will I end up with down here then? A 10 and a 5, right? Okay. Then I substitute in 0, so this term really didn't matter anyway. Okay. And what do I end up with for an answer this time? I end up with 10x. Okay. So let me write both of them down, and let's see if we can recognize the pattern here. So for the original function of 4x squared, we came up with 8x as its derivative. And for the function 5x squared, we came up with 10x. Okay. What is the pattern? Okay. How am I getting these numbers exactly? Okay. What we're doing? How did I get the 8? Well, I took 2 times 4. How did I get the 10? Well, I took 2 times 5. Okay. And if this process continues, it has been proven mathematically that this will continue to work. Okay. And so if I try to generalize this and I say, what is the derivative of some number times x squared, what is the answer to this question? Yeah. The answer to this question is take 2 times the a value and then times x. Okay? And this is a really, really nice shortcut because basically all we do is we take this 2 and we kind of pull it out in front. And we end up multiplying 2 times 4. And then what happens to the power of this? It drops by 1 unit, doesn't it? This original function was x squared. Now this function is linear. It's x to the first. Okay? And the really amazing thing about this is that this process works not only for x squared type equations, but if we were to go through and do all the math, it works for x cubed equations, for x to the fourth. It works for any power that we want. Okay? And so I want to look at just a general example here. And let's talk about what the derivative should be. If I gave you the function 7x to the third, and I ask you calculate the derivative of this for me, what is the derivative function for this? Okay? Yeah. What we do is we follow that same process. We bring this 3 out front, we multiply 3 times 7, and it turns into 21. And then what do we do to the power of the original? We decrease it by 1. Right. Okay? So the derivative function for this is 21x squared. And that's it. It's a very, very simple process. Now again, I'm not getting into all the mathematics behind why this works because I don't think that's the focus of this course. Okay? We saw a couple of really nice examples, some pretty easy ones that we did the math on, and now we're just jumping to the big conclusion that we can come up with. Okay? All right. What if we have an example like this? 10x to the 7th minus 5x to the 4th. And we want to know the derivative function for this, or the slope function for this. Okay, well, what is it? 70x to the 6th, 20x to the 3rd. Exactly. And it's that quick, we don't have to do any of this limiting definition anymore whenever we have a polynomial. Okay, we've got this nice little shortcut that works. Okay. All right, so any questions with this? The two-step process is always multiply the power, or bring it out in front and multiply it by whatever number's out here, okay, and then decrease the power by 1. That's the rule that you'll have to remember. Okay. Now, the nice thing is that not only does this rule work for polynomials, it has also been proven to work for equations that look like this. Square root of x. This also works for equations like this. Now, square root of x doesn't seem like it has anything, or doesn't look a lot like any of these examples up here, but it actually does. Because how can I rewrite this as a power? X to the what? To the 1/2. And now I can use the same process because I have x to some number. Okay? So what would be the derivative function for x to the 1/2? Okay? Well, I pull that 1/2 out in front, and what am I multiplying by this time? Since there's no number out here, I'm just multiplying by 1, right? Okay, so 1/2 times 1 is just simply 1/2. And then what do I need to do with the power up here? What did we do with this 7? Well, we dropped it by 1 unit, didn't we? I need to do the same thing here. If I take 1/2 and I drop it by a full unit, where am I at? Negative 1/2. And so the derivative function for the square root of x is 1/2 times x to the negative 1/2. And that's our answer. Okay? Another example. What if I give you the function 3 times x to the 0.6? Again, this works the same way. What is the derivative function for this particular equation? Okay, well, what's the first step that I need to do? 3 times 0.6, right. The 0.6 comes out front. I multiply it times 3. What is that? 1.8. And then what happens to the power of 0.6? Decreases by a full unit. And so what's 0.6 minus 1? Negative 0.4. Right. And it is okay to end up with negative powers up here. That's fine, because mathematically what this is saying is if I was to rewrite this, it would be 1.8 divided by x to the positive 0.4. Okay? So all this means is that just when they went through and they calculate this big old derivative here with the definition, what happens is they just end up with something in the denominator instead of up in the numerator. That's all that's happening. Okay? All right. So hopefully you'll feel comfortable not only with nice numbers here, but even if we have fractions or decimals, this process still works very well. Okay? What if we have an example like this? X raised to the pi. Even if we have irrational numbers, we still can follow the same process. What's the derivative function for this? What happens with this number? Comes out front, doesn't it? Okay? I multiply it times whatever's out here. In this case, there's just a 1. Okay, so pi times 1 is pi. And then what do I need to do with this power? Pi minus 1. I just need to decrease it by 1, right? And again, I don't know what the decimal, will be 2.14 instead of 3.14. Okay? But that's all we have to do. Okay? This process is the same no matter what this number is up here. As long as we just start with x to that power, then we're in good shape. All the derivatives work the same way. Okay? So the final generalized rule, okay, if I want to give you this rule here, if we have x raised to some power, okay, what is the derivative function for x raised to some power, no matter what the number is? What do we do at the end? Well, it comes out front, and then what do we do with the power? Decrease it by 1. Right. So the rule that you will see in your textbook is this one right here. Okay? Okay? And the name of this rule, and this is pretty common no matter which textbook this is, usually it's called the power rule. Okay? It tells you what to do if you ever have an equation that's got a power. This is the process for using a derivative, okay, or finding a derivative. Now, be really careful because it only works for these types of functions. If I ever have something else up here, if I come back to this example, if instead of this just being a 0.6, if it's a 0.6x, or anything else that's messy up here, then I cannot do this process. I can't just bring down a 0.6x in the front and finish it off because this is not the same initial setup as what we had here. It only works for setups where we have x to some number, not to a function. Okay? We'll have to talk about later what do we do in a case like this. That's a different rule. Okay? All right, so any questions with this derivative rule? Really a pretty simple rule. Okay. Let's see here. I need to pick out a couple more examples here. Let me look and see which ones I haven't done yet. All right, what if I do an example like this? Okay. 9 divided by x to the 4th plus 5 minus 6 x to the 3 halves. Okay, so we're going to have different scenarios here that we'll set up. First thing that I want to mention, notice this is the original function. We got x's and y's. Okay? A lot of times when we're talking about writing a derivative function, sometimes we use f prime of x. Other times we will use dy dx. Just again, it's saying that it's a slope. We're looking at the difference in the y's over the difference in the x's. Okay? So it doesn't really matter. Just if you see this notation, if it says find dy dx, it's just asking you to find the slope. Okay? All right. What are we going to do with this first component right here? How can we make it look like x to some number? Good. Okay? I think what we want to do is rewrite this equation as 9 times x to the negative 4. Okay? What I just showed you a little bit ago here, if we have negative powers and we move them to the denominator, they become positive. I'm doing the exact opposite here. Okay? I'm taking a positive power and moving it up to the numerator because now I can use my little shortcut rule. What's the derivative of 9x to the negative 4th? Okay, well, negative 4 comes out front. What's negative 4 times 9? Negative 36. X now goes to what power? And just be careful here. Negative 5. Remember, we need to subtract the full unit, and so negative 4 minus 1 is negative 5. And so the derivative of this 9 over x to the 4th is negative 36 x to the negative 5. Okay, what's the derivative of 5? 0. Okay, because 5 is a horizontal line, and the derivative of a horizontal line is 0. So I really don't even have to put anything in here. I don't have to put a plus 0. Okay, what about the derivative of this one? Okay, well, again, follow the same process. What do I do with this 3 halves? Comes out front, multiplies by negative 6. What's negative 6 times 3 halves? Negative 9. Okay. X, the power has to change. It has to decrease by a full unit. So what's 3 halves minus a full unit? 1 half, right. Okay. 1 1/2 minus 1 would just leave 1 half left. And this is our answer. Okay. So this is our derivative function in this particular case. And this is really nice because now we can jump ahead and we can do things like writing tangent line equations, and it's a lot faster. Let's just take this example here. What if we have this equation and we want to know the equation of the tangent line at x equals 1? Okay. We've already done the hard part. We've already calculated the derivative. What's the one thing that I can gain from this derivative, though? I'll gain the slope, exactly. That's the one piece that I will gather. So if I substitute in 1 wherever I see an x here, what's the slope of this function at 1? Okay, well, let's plug it in and see. dy dx, and I'll just put down here at x equals 1 just to remind myself that's what I'm doing here. Negative 36, 1 to the negative fifth, minus 9, 1 to the 1/2. I'm just substituting in 1. Okay. Well, what's 1 to any power? What's 1 to the 10th? 1. What's 1 to the 50th? 1. Okay. What's 1 to a negative number? 1. What's 1 to a fraction power? 1. Right? It's always 1. Okay. So this turns into negative 36 minus 9. So it looks like my slope is negative 45. Okay? So apparently what happens, if we were to graph this on our calculator and look at the value x equals 1, our graph would look something like this. Okay? It's going to be really, really steep at that value because I have a slope of negative 45. So my graph is almost going to be vertical at that point because I have a really, really steep negative slope of negative 45. Okay? Now, to finish off writing the equation of the tangent line, what else do we need to know besides the slope of our function? Well, we have to know some other point that the graph goes through. We have to know an x and a y coordinate. Okay? Let me make some more room here. All right. So in this case, I know the x coordinate is 1. Because that's the one point that we care about in this problem. What's the y-coordinate at x equals 1? Where do I get that from? Well, I don't get it from here because that's where I found my derivative, so the only other choice is from the original function, and that, of course, makes sense. Okay? So what if I plug in 1 here? This is just a 9. 9 plus 5 is 14 minus 1 to any power is just 1, so 14 minus 6 looks like 8. So it looks like my ordered pair is 1, 8. So back down to my graph here, if I was to plot this point, I would be at 1, 8. And now I need to write the equation of this line. And the form that I recommended toward the beginning of class was this one right here. Y minus y1, m times the quantity x minus x1. What value goes in for y sub 1? What's the y-coordinate? Yeah, 8. What's the slope value that we came up with? Negative 45. And what is the x-coordinate that we're interested in? 1. Okay, so this is a possible equation for the tangent line. Okay, and it would go right through the point 18. Okay, questions with writing tangent lines? Okay. The big thing that we have gained today is we have gained a process that will help us find this derivative a lot faster. We don't have to go through that whole definition if our equations are in a nice form. And we've seen that this nice form really works well for lots of different types of equations. Fraction powers it works well for, negative powers it works well for. I mean, there's lots of numbers that this will work really well for. Okay. All right. Next thing I want to look at is just some applications here. Let's see here. Here we go. Okay. The question says that a ball is thrown vertically upward from the ground at a velocity of 64 feet per second. And then they give an equation. Its distance from the ground at t seconds is given by this particular equation. H of t is negative 16t squared plus 64 times t. Let me go ahead and define the variables here. Okay. The t in this problem is one of the variables, and then the h is the other variable. What do you think t is probably in this problem? Time, right. Okay. In a lot of these physical science problems, we'll instead of having x's, we have t's, just to remind us that we're dealing with time here. Okay. What is the h in this problem? Did you pick that up as I was reading it? Height. Yeah. Okay. All right. So if we take a value for t and we substitute it into this original equation, it will tell me how high the ball is at that particular time. So if I plug in 1, after 1 second, I will know how high the ball is. Okay, and so forth. All right. Now, the actual question says, how fast is the ball moving 2 seconds after being thrown? Okay. And the key thing here is they ask the question, how fast is the ball moving? So is that really just asking us to take 2 and plug it into this equation? No, they don't want to know how high the ball was after 2 seconds. They want to know how fast was it moving. Thinking back to, just your physical science courses, what does it mean when we talk about fast? What are we referring to? What concept? Okay, speed, which is distance over time. Right, exactly. Okay, so we're just looking for the speed of the function. What's the speed of the function in terms of calculus? Okay, the big connection is that speed is a rate of change. Rate of change is a slope. Slope is a derivative. So we make the big connection here. We had to go through all the chains, all the links in the chain. But basically, when we talk about speed in calculus, we are talking about a derivative. Okay? So all we have to do here, first of all, is find the derivative function. Okay? And let's use our little shortcut rules from before. What is the derivative function for this first part? What do I do with that 2? Comes out front. 2 times negative 16, negative 32. What happens to the power? T to the what? To the first, because it decreases by 1. Okay? Okay, so I took care of the first one. Now I go after the next part. What's the derivative of 64 times t? 64, right. If this was just a linear equation, 64 times x, then my slope would always be 64. Okay? So here's my derivative function. Now, what's the value that we care about? Well, we care about 2 seconds. So I'm going to plug in 2 for my time component. And, this is an interesting one. What do I get for an answer? I get 0. Okay, now here's the big question, though. Interpret that 0 for me. What is 0? The speed of the ball is 0, which means that after we throw the ball up, when would it have a speed of 0? When it's right at the peak and it's beginning to come back down, isn't it? Okay, so what we have found here is we have found the place where the ball reaches its maximum height, haven't we? Okay, because its speed is 0. All right, just thinking about the graph real quickly. Okay, if I throw this ball up in the air and after 2 seconds it hits, okay, when should we expect the ball to hit the ground? When it's coming back down over here, wouldn't that have to occur right at 4 seconds? If it hits its peak after 2 seconds, should hit the ground back after another 2 seconds or 4 seconds, right? So we can do lots of analysis with this just by having a nice little shortcut for our derivatives. Okay. All right, we'll see you next time.